Yeah, good morning one and all. This is Nagajyoti working as an assistant professor in Department of ECE in St. Peter's Engineering. So today in this session I am going to discuss about classification of codes and its properties. Coming to the codes, so in the last sessions we have discussed about what are the different types of number systems, how to convert from one number system to other number system, and what is the significance of complements, what are the different methods in case of complements, and one's complement and two's complement. So in this session, I want to discuss about codes. So a group of bits in the form of zeros and ones is called as code. In case of a code, basically these codes are classified into two different ways. One is numeric and the other one is alphanumeric. The name itself indicates numeric. So in case of a binary codes, if the complete code consists of only zeros and ones, such codes are called as numeric codes. If a code consists of alphabets followed by numbers, such codes are called as alphanumeric codes. So in case of a numeric codes, we are able to represent the complete given number only in the form of zeros and ones. But whereas in case of an alphanumeric codes, along with the numbers, we can represent alphabets of capital letters A to Z as well as lowercase letters A to Z with some special characters. Coming to the numeric codes, in case of a numeric codes, these numeric codes are classified into different categories. The first one is weighted code. So here the name itself indicates each and every individual digit is having some weightage. So let me take an example of a decimal number 532. So in case of a decimal number 532, this 2 represents it is ones place, 3 represents tens place, 5 represents hundreds place. So each and every individual digit is having some significance and weight over there. That is the reason we can say that the decimal number is nothing but an example of a weighted code. So in case of a weighted code, if we interchange the given digits, whatever the output which we are getting, it is not a correct form. That is, we cannot interchange the digits in case of a weighted code. So the examples for the weighted code are binary and the second one is BCD. So in case of a binary, so here binary represents by, it consists of two numbers. Those two numbers are only zeros and ones. So here, in case of a binary, if I want to convert a decimal number of 5 into binary, which is a base 2, divide this 5 with 2. So 2 2's 4, remainder is 1. 2 ones 2, remainder is 0. So the equivalent of 5 in case of binary is 101. So this 1, 0 and 1, all these individual bits is having some significance. So these are nothing but an example of a weighted code. Coming to the BCD, next code is binary coded decimal. So in case of a binary coded decimal, so here we are not representing the complete bits as a division process. Here what we are doing is each and every individual digit is represented by its 4-bit equivalent. Now let me take 25. So 25 decimal number. If I want to convert this 25 into the binary, I need to divide this 25 with base 2. So the equivalent of 25 in binary is 1100 1. But if I want to do the same 25 in terms of BCD, so in case of a 25, it consists of 2 digits. So here the first digit is 2 and the second digit is 5. So if I want to write down 25 in terms of BCD, that is binary coded decimal. Here I am representing the two value, that is two equivalent in case of binary is 1 0, but instead of representing with 2 bits I need to represent with 4 bits. So here the 25 equivalent in case of BCD is the two equivalent is 1 0. If there are less than 4 digits over here, we need to append zeros. So double zero 1 0. Similarly, the 5 equivalent is 1 0 1. Here also I am not getting 4 digits over here. That is the reason I am appending one more 0. So in case of a BCD, if there are n digits in case of a decimal, the equivalent of BCD will be having 4 n digits. That is here 20. In case of 25, I am having only 2 digits. But in case of a BCD, 2 into 4, that is the number of digits multiplied with 4, because each and every individual digit is represented by 4 bits equivalent. So here, in case of a weighted code, the examples for the weighted code are binary as well as BCD. In case of a binary, just we are dividing the given number with the radix of the 2 and we are writing from bottom to top approach. Whatever the value which we are getting, we are representing the same thing in case of a binary. But whereas in case of a BCD, we need to represent each and every individual digit in terms of a binary with the equivalent of 4 bits. Coming to the next, which is nothing but classification of numeric code. The second one is non-weighted code. So here the name itself indicates we don't have any weightage for each and every individual digit. So the examples for the non-weighted code are XS3 code and gray code. So coming to the first one, which is nothing but XS3 code. So in case of XS3 code, the name itself indicates XS means adding, which is nothing but a greater than that. So here if I want to convert 25, which is in decimal number, into an XS3 code. So here we won't have any radix for the XS3 code. Here each and every individual digit should be added with 3. So here 25. For 5 we need to add 3. Similarly for 2 we need to add 3. So I will be getting 5, 8. Whatever the decimal digit which we are getting, we need to represent it as individually in terms of 0 segments. Or in simple words, the starting numbers are 0 to 9 in case of a decimal number. So here for 0, we need to add plus 3. So here 0 plus 3 is nothing but 3. The 3 equivalent in case of a binary is double 0 double 1. So here for each and every individual digit we need to add plus 3 and we need to represent the equivalent in case of a binary. Similarly, the decimal digit 9, XS3 code for 9 is 12. The 12 equivalent in binary is double 1 double 0. So here whatever the 58 which we are getting for 25, convert this 58 into a binary. How will you convert this 58 into a binary? Just divide this 58 with 2. Continue this process until we are unable to divide. And after completion of this successive division process, write down from bottom to top approach, that is nothing but an XS3 code. So here XS3 code is nothing but adding a 3 digit, that is adding plus 3 for each and every individual digit of a decimal number, and whatever the result which we are getting, convert that result into a binary form is nothing but called as an XS3 code. Coming to the next example for the non-weighted code is nothing but a gray code. So in case of a gray code, before going for the gray code, we need to know a gate which is nothing but called as XOR gate. That is nothing but exclusive OR gate. So in case of an exclusive OR gate, what we need to remember in case of a gray code is, whenever we are performing an XOR, the notation for the XOR is plus symbol over a circle. So here if we are performing a 2-bit XOR operation, here XOR is nothing but an exclusive OR operation. As I am saying it as a 2-bit, so if we are using a 2-bit, I will be getting a 4 different combinations, that is 0 0, 0 1, 1 0, 1 1. So if both the digits are same, the output is equivalent to 0. If both the digits are different, the output is equivalent to 1. Similarly, here also 1 0. So the result is 1. 1 1. The result is 0. Or in other words, I can generalize this statement in such a way that when the input is having odd number of ones, the output is equivalent to 1. When we are having even number of ones, the output is equivalent to 0. So we can say that the property of an XOR gate is it is used in order to generate an odd parity. Means whenever we are having odd number of ones, the output is 1. Whenever we are having even number of ones, the output is equivalent to 0. So in case of a gray code, what we are doing over here is the first number, whatever the binary number which we are having, we need to perform the operation of exclusive OR operation. The resultant is nothing but called as a gray code. So let me check it out with an example. So here I am taking a binary number which is nothing but 1010. So here this is a binary number. If I want to convert this binary number into a gray code, the procedure over here is write down the first MSB bit as it is. So here this is an MSB bit. I am converting binary to gray. So the procedure for this is first write down the MSB bit as it is, which is equivalent to 1. Then the second step is perform the XOR operation for the two consecutive digits. That is, the first digit is 1, the second digit is 0. 1 XOR with 0. 1 XOR, if I am performing exclusive operation for these two digits, here I am having odd number of ones, so the resultant is equivalent to 1. Similarly, perform XOR operation from the second digit with that of the third digit. So 0 XOR with 1 is equivalent to 1. Similarly, the third digit followed by the fourth digit, which is 1 XOR with 0, which is equivalent to 1. So whatever the resultant which I got is nothing but a gray code. So in case of a binary to gray conversion, the step 1 is first write down the first MSB bit as it is, then perform the exclusive OR operation for the two consecutive digits. If the two consecutive digits is having odd number of ones, the resultant is 1. If two consecutive digits are even, then the output is equivalent to 0. This is the way how we are converting a binary number into a gray code. So here we don't have any weight for each and every individual digit. That is the reason we are saying that the examples for the non-weighted codes are XS3 code and a gray code. Coming to the next type of code, which is nothing but a reflective code. So the example for the reflective code is a gray code. So before going for the gray code, first we should know what is the meaning of an reflective. So here it is nothing but a mirror image of the given number is nothing but called as a reflective code. So now let us see why only the gray code is called as a reflective code. Why we are not saying the XS3 code as a reflective code. So I want to write down only the 8 numbers for a gray code. So here I am assuming it as a 3-bit or a 3-bit number. So in case of a 3-bit, if there are 3 bits, I will be having 8 different combinations. So for 8 different combinations, I will be having from starting from numbers from 0 to 7. So first case, here I am writing a binary equivalent of 3-bit numbers followed by the gray codes. So here in case of a binary, the equivalent numbers are 0, 0, 0 to 111. Or in the other way, we can say that if there are 3 digits, the MSB bit should have 4 zeros followed by 4 ones. That is the equal, that is 0 to 7, this is the equivalent of 0. The 1 equivalent is 0, 0, 1. 2 equivalent is 0, 1, 0. 3 equivalent is 0, double 1. 4 is 1, double 0. 5 is 1, 0, 1. 6 is 1, 1, 0. 7 is 1, 1, 1. All these already we have discussed in case of number based conversions, how to convert a decimal number into a binary number. So here, as just I told you that how to convert a binary number into a gray code, the first step is write down the most significant bit as it is. So in the first case, the most significant bit is 0. So I am representing the first 0 as it is. Then perform the exclusive OR operation for the consecutive digits. So here the consecutive digits are nothing but 0 XOR 0. 0, 0 XOR 0. 0. Similarly, for the second number which is nothing but equivalent to 1. 1. First MSB bit is 0. 0 XOR 0. 0. 0 XOR 1. 1. Similarly, I am continuing this process for the decimal digits of 0 to 7 into the corresponding gray code. In the second one, that is the first MSB bit is 0, 0 XOR with 1 is 1 and 1 XOR with 0 is 1. So the two equivalent in case of a gray code is equivalent, in case of a binary is equivalent to 3 in terms of a gray code. Similarly, for 3, for the 6, the first MSB bit is 1, 1 XOR with 1 is 0, 1 XOR with 0 is 1. For the last one, 1, 1, 1. MSB bit is 1, 1 XOR with 1 is 0, 1 XOR with 1 is 0. Now, how I am saying this gray code is an example of a reflective code. So, split up this in such a way that among 8 combinations, the half of the 8 combinations is 4. So, I am dividing upper part 4 and the lower part as 4. So, if you observe this, in case of the upper part of the 4, all the MSB bits are zeros and all the MSB bits in the lower part are ones. Similarly, in the upper part of a gray code, the last 2 bits are 1, 0. These is mirror image for the lower code. Similarly, here it is 1, 1. It is a mirror image for this 1, 1. Here it is 0, 1. Here it is 0, 1. Here it is 0, 0. Means, if here I am taking an example of a 3 bit. So, in case of a 3 bit, leave the MSB bit or leave the 1 bit over here. Compare the remaining 2 bits with that of the lower half of the part. So, the last 2 bits will be the mirror image for the upper part. Similarly, if we are considering a 4-bit number, instead of considering 2 bits, there I need to consider 3 bits. So, the last 3 bits will be the mirror image of the upper part with that of the lower part. That is the reason gray code is also called as a reflective code. Coming to the next classification of a numeric code, which is nothing but a cyclic code, or it is also called as unit distance code. So here, if you observe the same conversion of a gray code, so here already I have done how to convert a binary number into a gray code. So if I compare one number with the next consecutive number, so the first number is 0, the next number is 1. If I compare the first gray code number with the next number, there is a change in a single bit position. That is only in the end. The first 2 bits, that is first bit is 0, second bit is also 0. In the second number also, the first 2 digits are same. There is change in only single bit position. That is the reason gray code is also called as cyclic code or a unit distance code. Not only taking 0 and 1, if you compare any 2 consecutive numbers of a gray code. Let me take these 2 numbers. So here the last 2 bits are same, which is nothing but 1, 0 and 1, 0. There is change in only a MSB bit. So how can we prove that a gray code is a cyclic or unit distance code is? considering any two consecutive numbers of a gray code. If we compare the two consecutive numbers of a gray code, there will be change in a single bit position. That is the reason gray code is also called as a unit distance code or a cyclic code. Coming to the next one, which is nothing but a classification of numeric code. The next category is sequential code. So the examples for the sequential code is 8421 code or an XS3 code. So here 8421 itself indicates here each and every individual digit is having some weightage. So if I want to represent suppose 3 in case of an 8421, by adding which numbers I will be getting a 3? By adding 2 as well as 1, I will be getting a digit of 3. So the 3 equivalent in case of an 8421 is under 2 we need to write down 1, under 1 we need to write down 1, and the remaining just place a zeros. So in case of an 8421 code, the maximum number which we can write in terms of a binary is 15, because 8 plus 4 12, 12 plus 2 14, 14 plus 1 15. So here the maximum or the highest number which can be represented with 8421 code is 15. So here in case of a 15, the equivalent is all ones. Similarly, in case of a 14, I will be getting triple 1 followed by 0. Why we will be calling this 8421 code as a sequential code is, if we compare two consecutive numbers of a 8421 code, the second number will be greater than that of the first number. That is the reason it is called as a sequential. Sequence itself indicates it is some order. So here if we compare the first number with that of the second number, the next number will be the incremented of the previous number. That is the reason we are saying that 8421 code is an example of a sequential code. Similarly, as we have discussed just now about the XS3 code, that is adding each and every individual digit plus 3 and representing the corresponding in terms of a binary is nothing but called as an XS3 code. So the valid XS3 codes are we won't have any 0 in case of an XS3, because for a decimal digit of 0 we need to add plus 3. So the starting number for the XS3 code is 3, and if I am taking a decimal digit of 9, the highest number which is equivalent to 12. So here in case of an XS3 code, the starting number is 3, the next number is 4. Even if we take the consecutive numbers in case of an XS3 code, the first is lesser than that of the second one. That is the reason XS3 code is also an example of a sequential code. Coming to the next classification of a numeric code, which is nothing but an error detecting and correcting codes. The name itself indicates error, means the complete this error detecting and correcting codes are used whenever we are sending a data. That is, in case of a communications, we are transferring the data in the form of zeros and ones. So error itself indicates here transmitter is nothing but where the information, at which point we are going to send our information is nothing but called as a transmitter. At which point we are going to receive our information is nothing but called as a receiver. So here if the transmitted bits are not is equivalent to received bits, then we can say that there is some error. Means the transmitted bits are not matching with the received bits, then such is nothing but called as an error. So here error detection. Here detection itself indicates we are going to find out where the error is present. So by using these codes we can find out where the error is present. Once we found out where the error is present, we can also able to detect or correct the error. So here the examples for the error detection and correction codes are nothing but parity codes as well as the Hamming code. So here the parity codes itself indicates if I am sending an information in the form of a zeros and ones, the actual information is nothing but called as a message bits. So whenever we are performing any transfer of information, we are not only sending an original information, along with the original information we are adding some other bits. That extra bits are nothing but called as a parity bits. So here the significance of a parity bits are nothing but these parity bits are used in order to find out where the error is present, and if you found where the error is present, we can able to correct that error by using the parity bits. So here parity bits are nothing but these bits are not the actual information bits. These are the extra bits which where we are adding to the actual information, and by using these parity bits we are able to find out where the error is present and how to correct the error. Coming to the parity, now let me take, I am using a 2-bit. So here 2-bit itself indicates we can able to write down 4 different combinations, that is 2 power n, as I am saying it as a 2-bit, 2 space, which is nothing but 4. So here the combination bits are 0 0 0 1 1 0 1 1. Now let me take, I am assuming that these are the actual information bits, but I am not going to send these actual information bits. Along with these bits, I want to use a parity bit. These parity may be either an odd parity or an even parity. So here, if I want to go off, these bits are nothing but called as message bits, and here I am adding a parity bit. Now, as I have told you, a parity bit may be an odd parity or an even parity. So here, if I want to make these parity bits as odd, so here the number of ones in the complete code word should be equivalent to 1. So in the message bits, I am having only 2 zeros over here. As I am saying it as an odd parity, I need to add a 1 over there. So the odd parity bit for 0 0 is 0 0 1. This one is nothing but called as a parity bit. Or in simple words, I can say that a parity is nothing but if it is an odd, the total number of ones in a code word should be equivalent to odd number of ones. If it is an even parity, the total number of ones in a code word should be equivalent to even number of ones. Similarly, in the second case, as I am having a single one which is equivalent to odd, so if I want to make this complete odd parity bit, I should not add a 1. Instead of adding a 1, I need to append a 0. Because if I am checking this complete combination 0 1 0, in case of a 0 1 0, here I am having only 1 1, which is nothing but an odd parity. Similarly, for the third condition, in case of 2 bits of 1 0, already here I am having a single one which is nothing but odd number of ones, so the parity bit should be equivalent to 0. Coming to the last one, here both the are 1 1, that is here I am having even number of ones, so the parity bit which I want to make use is nothing but an odd parity bit. That is the reason I will be adding a parity bit which is having a 1. So if I take all these ones, it should be of only odd. So here as it is a 3 ones, it is odd. As it is having single one, it is an odd. Similarly, if I want to do for the even parity, as here I am having 2 zeros, the even parity bit should be equivalent to 0. Or in simple words, if I am able to write down one parity, the reverse of that parity will be equivalent to that of the next parity. That is, if I am able to write down the odd parity, the reverse or the complement of an odd parity is nothing but an even parity. So this is the way how to add a parity bits. These parity bits may be either an even parity bit or an odd parity bit. Coming to the next one, which is nothing but a Hamming code. So here, this is a special type of code, or this is a method by which you can able to correct and detect the errors by using a parity bits. So in case of a Hamming code, we will be using a parity bits. By using those parity bits, we are able to find out where the error is present and how to correct the error. We will be discussing that Hamming code briefly in the next session. That is the complete deals with how to find out the error and how to correct the error by using the Hamming code. So in the next session, I will give you the brief introduction as well as the importance of a Hamming code and how many errors we can able to find out by using a Hamming code. So this is all about a classification of codes under the numeric one. Coming to the next one, which is nothing but an alphanumeric. So in case of an alphanumeric, it consists of an alphabets followed by the numerical numbers. So whatever the codes which we have discussed till now, in all these codes we are having only the digits of zeros and ones. That is the reason all these codes are an example of an numeric codes. But whereas in case of an alphanumeric codes, it consists of alphabets followed by the numerical numbers. So the examples for the alphanumeric codes are ASCII, that is American Standard Code for Information Interchange. So here ASCII represents American Standard Code for Information Interchange. The best example for these ASCII codes are we are using the computers. For these computers, we are adding a keyboard. So on the keyboard, along with the numbers, we'll be having an alphabets. But a computer will not able to understand the alphabets because it will understand only the machine level language. So here, whenever we are pressing a button on the keyboard of A, that should be converted into equivalent of only zeros and ones. So here whenever you are pressing any alphabet or special characters on the keyboard, it need to be converted into a binary equivalent. So there we will be using a ASCII code. So here this ASCII code is a 7-bit code in which we are able to write down capital letters A to Z as well as small letters A to Z and some special characters like dollar symbol, comma, double quotes, etc. So here, if I want to write down the ASCII code for capital A, the equivalent is here 66, and similarly for small a it is 96. So here this 96 we need to convert into the binary form. That equivalent is nothing but an ASCII code for small a. So similarly the ASCII codes for alphabets as well as special characters are predefined value by which we need to remember only the starting number and we will be adding plus. If I want to know what is the ASCII code for Z, in case of alphabets, we will be having 26 alphabets. So adding plus 25 for the corresponding will give you the what is the ASCII code for the Z. Similarly, the last one is EBCDIC, that is EBCDIC, which is nothing but extended binary code that for extended E represents extended binary coded decimal for information code. That is, in case of an extended binary coded interchange here, we'll be having a 8-bit. In case of an ASCII, we'll be having a 7-bit code, but whereas in case of an EBCDIC, we'll be having an 8-bit code. This is all about what is the classification of codes and its properties. So here properties are nothing but how can we say that a particular code is nothing but either a reflective code or a cyclic code. Just I'll give you a brief overview of this. So basically the codes are classified into two different ways. One is numeric code and the other one is alphanumeric. So in case of a numeric code, I'll be using only the numbers of zeros and ones. But whereas in case of an alphanumeric codes, along with zeros and ones, I'll be having the other more digits, that is nothing but alphabets followed by the numerical numbers. Again, these numeric codes are classified into weighted. So here weighted itself indicates each and every individual digit is having some significance. Means we cannot interchange the positions of those corresponding digits. The examples for the weighted code are binary code as well as BCD. Coming to the next classification, non-weighted code. So we won't have any significance for each and every individual digit, which is nothing but called as a non-weighted code. The examples for the non-weighted code are XS3 code and a gray code. So here XS3 code is nothing but adding +3 for each and every individual digit and representing in terms of a binary is called as an XS3 code. Gray code is nothing but performing an XOR operation for the two consecutive bits of a binary number is called as a gray code. The properties of a gray code are nothing but it is called as a mirror image code or a reflective code, because if we take any n bits, if we compare the n minus 1 bits on the LSB side, the half of the bits will be the mirror image for the upper part to the towards the lower part. That is the reason it is called as a mirror image code or a reflective code. Coming to the next one, which is nothing but cyclic code. So if we compare any two consecutive numbers of a gray code, there is a change in a single bit position. Such codes are nothing but an example of a cyclic code or a unit distance code. And coming to the next classification, which is nothing but a sequential. So if we take two consecutive numbers, the first number will be less than that of the second number, as it is forming an increasing order path. It is nothing but called as a sequential code. The examples for the sequential codes are 8421 code and XS3 code. Coming to the last classification of numeric codes, which is nothing but error detection and correction codes. These error detection and correction codes are basically used in case of a communications where we are transferring our information in the form of zeros and ones, that is in terms of an encryption and decryption of the data, and these codes are used in order to find out where the error is present, and if once we found out where the error is present, we can able to correct that error, because already we have detected where the error is present. So in case of an error detection and correction codes, the examples for the error detection and correction codes are parity as well as a Hamming code. And all, these are all about the numeric codes. Coming to the alphanumeric, ASCII, that is American Standard Code for Information Interchange, which is a 7-bit code in which we can able to represent the alphabets of uppercase as well as the lowercase with some special characters. And EBCD, that is extended binary coded decimal for information interchange code, is nothing but an EBCD code, which is an 8-bit code. That is advancement for an ASCII code is nothing but an EBCD code. These are about the classification of codes and its properties.